Now, whenever an electric current flows through a conductor, electrical energy is used up, and we say that the current is doing work. So, we know now that the rate of doing work is called power. So, here electric power is nothing but the electrical work done per unit time. That means the rate at which the conductor is doing its work is consuming the energy. That rate of doing work is known as electrical power, or you can say electric power. So, if we look at the mathematical formulation, power is nothing but the work done divided by time taken. Power is represented by P is equivalent to W by T. Now, let's talk about the units of power. If we look at its units, the unit of work is joule, so J, and the unit of time is seconds. So, joule per second is the unit of electric power. But this joule per second is equal to the watt. So, the SI unit of power is watt, represented by W. So, it means the 1 joule per second is nothing but it is equal to the 1 watt of power. If we need to define 1 watt of power, so the rate of working of 1 joule per second, that is, see, work if work done is 1 joules and time taken is 1 second, then 1 joule divided by 1 second is nothing but that is 1 watt of power. Now see, this watt is the smaller unit. So for a bigger unit we are using kilowatt, and the bigger unit of power is kilowatts, and this unit is used for commercial purposes, and this 1 kilowatt is equal to the 1000 watts. Now for whenever work is done, an equal amount of energy is also consumed. Some work is done whenever current flows, and when work is done, an equal amount of energy is also consumed. So we can also say that electric power is the energy consumed per second, because work and energy as per law are equal. So that is why we can replace work done here by energy. So this is another definition for power, that you can say that electrical power is the rate at which electric energy is consumed, or you can say it's the electrical energy consumed per second. So whenever electrical appliance consumes 1 joule of electrical energy in 1 second, that means we are having a power of 1 watt. So we have given two definitions for power. So we can combine both these definitions as the rate at which work is done or the rate at which electrical energy is consumed is called electric power. Now let's look at the different formulas for calculating power. See, we know that now that power is nothing but that is equal to work divided by time. Okay, and we have studied that work done by the current I, when it flows from time t under a potential difference V, that work done is equal to V into I into t. We know that work is equal to V into I into t joules. That much of work is done when current I flows from for time t under the potential difference of V. We can substitute this value of W in equation first. So what will we get? Power as it is. Instead of W, we will write V into I into T and then divide by T. T will get cancelled out and you will remain with P is equal to V into I joules per second. Or you can say instead of joules per second, that's watt, because joule per second is equal to watt. So our power is equal to V into I watts. Here V is potential difference in volts and I is current in amperes. So you can whenever the power in watts can be found by multiplying the potential difference in volts by the current in amperes, and you will get the power in watts. Now let's look at another formula. That formula is in terms of current and resistance. Okay, now again here from here P is equivalent to V into I. So I have written here P is equal to V into I. Now by Ohm's law, V is equal to I into R. So substitute this V here. P as it is. Instead of V, we have written I into R, then I. So we will get I square of I and resistance. So what we get from this, that power is equal to the square of current multiplied by resistance. So this is in terms of current and resistance. Now if we calculate the formula in terms of V and R, potential difference and resistance, again the same formula, P is equivalent to V into I. From Ohm's law, we can have now I is equivalent to V by R. So substitute for I, V as it is, and instead of I we have written V by R. So we will get P is equivalent to V square into V square divided by R. So this is the another formula for electric power. So in this way we got through three formulas for power. One is P is equivalent to V into I, that is potential difference into current. V square divided by R, that is square of potential difference divided by resistance. I square into R, that is square of current into resistance. Now let's have the power voltage rating of electrical appliances. See, every electrical appliance, like if you talk about radio, bulb, fan, there is a label or there's kind of engraved plate there which tells us about the voltage that is applied, that is to be applied, and the electrical power consumed by that appliance. So that rating, that label which is present there on every electrical appliance, that rating, that label is known as power voltage rating. See, for instance, if you look at the particular bulb in your home, maybe it will have the figure of like this 100 watt and 200 volt written on it. Now this 100 watt, it means that the bulb has a power consumption of 100 watts, and 220 volts means that it is to be used on a voltage of 220 volts. So basically this power rating, this is known as power rating, the label which is present on the appliance. This power rating tells us the rate at which electrical energy is consumed by the appliance. So the usual power rating of some appliances is like the tube light has usual power of 40 watts and usual voltage of 220 volts. In bulbs, usually normally the power is 100 watts and the voltage is power is 60 watts and the voltage is 220 volts. So there is already a power rating done on the appliances. Now let's look at another important thing, that is formula for calculating electrical energy. Now we will derive a formula for calculating electrical energy in terms of power and time. Now see, we know that power is equivalent to work divided by time, or power is equivalent to energy divided by time. Now if we want to power is equivalent to work divided by time, as we studied right now, power is nothing but work divided by time, and as per law of conservation of energy, work done is equal to the electrical energy consumed. So we can replace here work by energy. So we can write it down, power is electrical energy divided by time. That means electrical energy is power into time. So it means that electrical energy consumed by an appliance is given by the product of its power rating and the time for which it is used. So we can say that electrical energy depends on two factors. One is the power rating of the appliance and the time for which the appliance is used. So we can use this formula for calculating electrical energy. Okay. Now let's talk about units. The unit of power is watt and the unit for time is hour. So it means the unit of energy, electrical energy, is watt hour. It's represented like this. Okay. But let's look at first 1 watt hour. 1 watt hour is the amount of electrical energy consumed when an electrical appliance of 1 watt power is used for 1 hour, because we saw that energy is power into time. So that means the appliance has the power of 1 watt and that appliance is used for 1 hour. At that time, the appliance definitely is consuming the energy of 1 watt hour. Now for commercial purposes, we are having another unit, that is kilowatt hour. The SI unit of electrical energy is actually joule, right? And we know that 1 joule is the amount of electrical energy consumed when an appliance of 1 watt power is used for 1 second, right? In case of joule. So that means power is 1 watt and time is 1 second. But actually, joule represents a very small quantity of energy, and therefore it's inconvenient to use where a large quantity of energy is involved. So, for commercial purposes, we are having a bigger unit, that is kilowatt hour. And 1 kilowatt hour is the amount of electrical energy consumed when an electrical appliance having a power rating of 1 kilowatt, not 1 watt. It's 1 kilowatt because 1 kilowatt consists of 1000 watts. So when one power rating of the appliance of 1 kilowatt is used for 1 hour, okay, and 1 kilowatt is equal to, that means 1000 watts, okay. So for commercial purposes, we are using the unit of electric kilowatt hour. Now, if we see the relation between the unit kilowatt hour and the joule, that means how many joules can make 1 kilowatt hour. So let's have a look on this. See, 1 kilowatt hour. That means the amount of energy consumed at the rate of 1 kilowatt for 1 hour. I have written here for 1 kilowatt, I am writing here 1000 watts because 1 kilowatt means 1000 watts. So that means the power at the rate of, energy consumed at the rate of 1000 watts for 1 hour. Now we know that 1 watt is equal to 1 joule divided by 1 second. So we can replace in this equation as 1 kilowatt hour, then instead of 1000 we will write 1000, then for 1 watt here we can write 1 joule divided by 1 second because watt is equal to joule by second. So I am writing a joule divided by second, then for 1 hour. Now we know that 1 hour is equivalent to 60 minutes and 1 minute is equivalent to 60 seconds. So we are trying to convert this 1 hour into seconds because joule is the smaller unit, so time should be in seconds. So then 1 kilowatt as it is, 1000 as it is, joule divided by second as is, and for 1 hour I am writing here 60 into 60 seconds. Okay, if we solve this, we will get 36 lakh joules. That means 3.6 into 10 raised power 6 joules. So you can see here that 1 kilowatt hour is equal to that much of joules of electrical energy. So you can see when that much of joules energy is there, then we can say it makes 1 kilowatt hour. So here you can see kilowatt hour is the bigger unit and joule is the smaller unit. So we are using kilowatt hour as the unit of electrical energy for commercial purposes.